Welcome to the Nether, nerds. No, not a great one. Didn't feel great. That's okay. Not going to restart. We own it. Here we go. The example f and f prime on the same plane. Yesterday, we actually calculated out the derivative. This one is going to be a weird name of an example, but I'm going to call it what if we don't define f of x. And what I mean by this is we're going to get a graph, and we're going to be told that it's f, but we never get f of x equals anything. So there's nothing for us to even plug in and calculate the derivative to make sense of it. Okay, we did a very, very similar problem to this yesterday for the bell ringer. We're going to refine that idea a little bit today. So here we go. Let's say that we have, without any super specific numbers, our first one, we're going to give ourselves a nice graph, or an ugly graph, I haven't decided, of f. So here we go. No numbers. All we need is the same general shape. All right, so I have a lovely coordinate plane here. And let's say I have a wonderful function that does something. And we're going to make it a smoother curve. Something like this. That's f of x. No numbers needed. Now, our goal and where we're going with this is just from this graph of f. Anybody know roughly what it might be equal to? F of x equals something. Like no real specific numbers, but I think I have a pretty good feeling that it's x to some degree that maybe we'll all agree with. It looks like a cubic to me. How many roots or x-intercepts does it have? 3, so that's a good indication that maybe it's x cubed something. There's probably other stuff, x cubed plus x squared. Like, don't care about the other stuff, but I think it's a cubic. All right. As we go through this, we want to be able to graph f prime only from this picture, which is, if you hate limits, that's a good thing because we don't have to use the limit, but we need to be able to make sense of this. I'm going to be drawing a bunch of things on here. You don't need to draw them all, okay? You can obviously, but we don't have to. We're going to graph f prime. Graph f prime of x, the derivative of a function. Now, I wish that I could do this with a good animation. Which board is easier for everybody to see? Probably that one. Okay, check it out. I'm going to work through this, and I'm just going to move this with my tangent lines, okay? Just so we can kind of get a feel for what it looks like. If I'm here, that's my tangent line, right? As I slide up, my tangent line starts to do this, and that looks like it's super special. The tangent line here has a slope of 0. So if I said, what's the value of the derivative right here, it's the same as me asking, what's the slope of this line? Do you guys all agree that it's 0 here? So if I wanted to plot the derivative right there, and I will put this on here. You don't have to draw this one. My red points are going to be f prime. Only red is the only thing you have to draw on yours. So we'll use this purple color. Right here, I think that the slope, m, is 0. Is there another place where the slope is 0? Hoot and holler. Is it hoop or hoot? Probably hoot. Hoot and holler? What? That sounds like a very Dutch word. Anyway, shout it out when we get to another place, hoot and holler, rather, when we get to another place where the slope would be 0 of the tangent line. Right here? Hoot. Okay, cool. I'm going to draw out that one there. Can we all agree that the tangent line at these two places, the slope m, or f prime of whatever, would be 0? Everybody agrees. Is there anybody who does not quite understand why that's the case? So check it out. If f prime is just the function that gives me all of the slopes of the tangent lines, right at this x value, what did we just decide the slope was? So right at that same x value, I'm going to give the derivative a value of 0. At this x value, the slope of the tangent line was 0, so I know that f prime of whatever this is also 0. We just got 2 points on our derivative because all I'm doing is plotting where is this the slope. Here it's 0 and here it's 0. So a maximum or minimum, absolutely. Turns out later when we graph big ugly functions that maybe we didn't in algebra or pre-calc, maybe that is going to be super valuable for us. Like it will be. We can graph some nasty functions really easily with calculus. All right. Well, let's do a little bit more thinking. We're not going to have numbers because I don't have a scale, but you can tell me for little parts, positive or negative slope. Right here. Positive or negative? Now, as I get closer and closer to that maximum, is my slope getting more positive, steeper, or less positive? So it was really positive, and now it's less positive, and then eventually gets to 0. As soon as I move past this, what types of slopes do I start experiencing? Negative. Now, you tell me, and this is going to be a weird one, some tangent lines, they look strange because we only care about touching one point in some region. So like this line doesn't look like a super tangent line because it touches multiple times, but if we just zoom into right here, it is touching just once, right? Do you guys agree that the steepest or the most negative slope that I ever get happens about right, I don't know, right there? Because it was getting more negative, and then we hit what's known as an inflection point, where it stops from curving like this to it starts curving like this instead. And then it starts getting less negative again. Everybody see that happen? Which means, do we all agree that at this point right here is where my slope was the very most negative? Everybody's still cool with that? So I don't know the value of it, but if this is the very most negative, I'm just going to go down and say, okay, well maybe it's here. This is pretty negative. Everybody cool with how I got roughly that point? There's no real number, but it's the most negative. That's the lowest point that's ever going to happen. Okay, let's keep thinking about this. I'm going to focus back on this side. I'm just going to use the lines on the screen, and I'm going to be clever with this. Because check this out. This thought has never crossed my mind. But I'm going to draw a bunch, I'm going to draw a bunch of tangent lines in green. What is going on? It's not invisible. It's right there. Okay, scratch that terrible idea. Okay, we saw that right here it's super duper positive. And a little less positive. And a little less positive still. If I just plot those values, super duper positive, all the way up here, right? Like a really high slope. And then as I get closer, it starts going down a bit more. And down a bit more until eventually it gets to a slope of what? 0. Does it look like these points, does it say that the slope was really big and then a little smaller, until it gets to 0? In this whole region, again, only red is the one that I want on your page. In this whole region, what is the slope? Positive or negative? In that entire region, it goes negative, right? Now, it's just a little bit negative on this line. And then it gets more negative, and then it got most negative right underneath this. And then it starts getting less negative or closer to 0 again, right? Now, I'm just eyeballing these points the best I can, but it got more negative, a little more negative, and then it started getting positive again. And this isn't going to be perfect, but how about from this point on? Is it still positive or negative on all of these? Now, it starts just a little positive, and then it starts getting way more positive, right? So let's do that. It starts getting a little positive, and then it gets more and more positive as we go. All right. When I connect all these points, can you tell me the shape that it's going to spit out? It kind of looks like a parabola, and I'm pretty confident that it is. I'm going to connect these as best I can, and we're just sketching, but it certainly does look like a parabola in here. And I'm going to try that again because I don't like that point. I'm trying to make it not pointy, but that's okay. Now, this is a good sketch of the derivative. And here's something that we're not going to hit super hard today, but I want to make sure we all have it in mind. Yesterday, when I gave you f of x, and you don't have to write this as just review, or even today, we had f of x is 2x plus 3. F prime of x was just 2. Do you agree that this is an x to the first power? And 2, it seems weird to do this, but it's x to the 0. It seems like in that situation, that one very specific context, my degree just went down by 1, right? And then just now, we claimed at the beginning of this problem that f of x was some type of x cubed, plus who cares? And when I did f prime, I don't know the exact equation, but it kind of looks, you guys said, like a parabola, which means that I would probably assume that f prime of x is x. Does it seem to just kick down again? If I were to graph, or if I were to, like, we're not going to graph this one right now,
But hypothetically, if I had f prime of x with something x to the fourth, any guesses on what f prime of x might be? Something x cubed. And you would be right. There is a pattern showing up here about the rate of change and its degree of the polynomial that represents it. It gets really ugly with the language, but there's something hiding here, and I'm starting to see that trend show up. Okay, we will cover that trend in super duper detail soon. Before we do that, I want you guys to try to graph a derivative for me without the actual function. Now, everybody's favorite thing or least favorite thing is always absolute values, so I'm going to hook you up with an absolute value. I promise it's really nice for these. Super duper nice. All right, on B, I want you guys to logic and reason out with each other independently, with me if you need help with it. I'm going to give you a graph of an absolute value. And we can make it whatever absolute value we want. I'm just going to make it super duper nice. We're going to do it here. So there's an absolute value function, and I did not mean to change colors. This dark red is f of x. I want you guys to sketch f prime. I'm going to do mine in purple, but I'm going to give you guys a moment. I want to see what you come up with. Chat it out. We'll go like 1 or 2 minutes, and then we'll discuss and see, hopefully, that everybody has it, but if not, how easy it can be. Cool. I'll give you guys a little bit of time. Okay, so as I'm looking at this, do you want to trust the scale here or not? Like, should I assume that this is the point negative 1, 1? I can, and we don't need to, but if we want to, maybe it'll help make sense of it a little bit. If these are, in fact, just 1, negative 1, 1, and negative 2, negative 2, 2, and negative 3, 3, so forth and so on, can you tell me the slope right here? It'd be a negative 1 if we trust our scale, right? How about here? How about here? Literally anywhere along this line, what is the slope that we just found? How do I draw the graph of a function whose value is always negative 1? It's a line at negative 1. Now notice, I'm not going to get quite to 0, but I will annotate in a different color. The slope, and I'm just going to say m, is always negative, and I'm just going to do it like this here. Now, we use negative 1 just as a nice number to make sense of, but I think that as soon as we look at it, everybody can agree that everywhere in this, the slope is negative, and it's the same negative number. All right. What if we switch gears and notice, not quite here. What if we switch to this side? If I were to take the slope here, or here, or here, or here, or here, doesn't matter. The slope is always what? 1, or positive 1 in this case, right? If we trust the scale, we would say the positive. Can we draw a line that's always positive 1? All right. Notice, again, I'm not going quite to the x-axis yet. This purple graph that we've just drawn is almost all of f prime. And there's something wonky that happens. Okay. This always looks silly to do. I'm going to use this board because I have a little bit easier time getting over it. If I draw the tangent line at this point, right here, I'm going to crack it. It's going to happen. You agree it's this? Okay, and here it's this now. And here it's still this. What happens here? Where it's pointy. I mean, I don't know. Maybe it comes from this side, and then it's definitely not going to be this. It's either this or this, right? It depends on which side that we're coming from. Real quickly, just to connect, we haven't done a limit yet. A derivative is just a limit. Everybody agree with that? For the purple function that we'll call the derivative, I'm fine with it. Does the limit exist? The limit doesn't exist when x is 0 because we have what type of discontinuity? So if the limit doesn't exist and a derivative is defined as a limit, what do you think we conclude about the derivative at that point? It doesn't exist either. Because when we try to do the math for it, this thing, it's fine, it's fine, it's fine. It gets here and it just goes bonkers. It can't decide what it wants to do. And it shouldn't. It can't. It doesn't exist. How do we indicate on our graph that my derivative never exists when x is 0 in this case? We have an open dot, and we have an open dot. Here is our derivative. Now, as we go through this, what we see right off the bat is for the first time we've noticed and found a spot where the derivative doesn't exist. Okay, my function was continuous. The function, everything was cool with it. The derivative was not. They're different in this case. That's okay. They won't always be different, just like we saw here. The function was continuous. The derivative existed everywhere. It was also continuous. There are some weird little things that happen. Can a derivative fail to exist? Absolutely. In fact, there are specifically 3 ways that this can happen. I don't have my notes from yesterday. Can somebody tell me the bullet point that we're working under? Graphing a derivative? Okay, so while we're looking at this, it's related. We worked this out with the graph. This is a new bullet point, though. I'll go back to black. It turns out that there are places where f prime of x just doesn't work. So we're going to say when f prime of x is undefined. That is a more clean way of saying does not exist. But there are places where it can happen. Now, very specifically, we saw one particular example. What happens on the graph of f, on this red graph, that led to this not existing? Like specifically, if I said what goes on with the red graph right here in this little spot, how would you describe what we're looking at there? Does it turn? I mean, kind of. It turned from going down to the right and up to the right now, right? So I'd argue that it did turn. Was it a smooth turn? Instead of smooth, what might we call it? It's a sharp turn, right? Okay, so we have when f prime of x is undefined. Turns out there are 3 ways this can happen. 3 ways this happens. Okay, the first of these is that sharp turn. So I'm going to have all 3 right here. Excuse me, all 3 right here. The first of these, sharp turns. Now, when we're looking at this, there's always some gray area to whether we actually talk about the derivative or we talk about the limit. But here's the thing. Are they really any different? The derivative is defined as a what? It's a limit, right? So whether we call it the derivative or the limit, it doesn't matter. It's the same idea. At a sharp turn on the graph of f. So on f. This derivative does not exist. And I'm going to sketch essentially like the same picture. So right here, I'm just going to move my graph around. At this point right here, f prime is undefined. And I'm just going to call this c. When we get a sharp turn, whether it's 1 or 2 or 3, doesn't matter. We're going to say f prime of c is undefined. Now, to make it a little bit more familiar, to look like something that we've already talked about, show me with your hands when a limit doesn't exist. So there's a bunch of ways, right? Here's the most common way, though, the jump discontinuity. We have a jump discontinuity happening with my derivative. What we can say is, and this is informal, but I'm going to claim that the left, what's my shorthand for derivative? d dx. d over dx is the shorthand that we're going to use. We'll see why. If you want to use it, you're cool. But the left derivative, in this case, was not equal to the right derivative. Okay. If we wanted to be wordy, and you can, I'm not going to write it down, but this is no different than saying that the left, instead of calling it a derivative, what do we say we could call it instead? The left limit is not equal to the right limit, and we can see the limit doesn't exist. Cool. Exact same logic with my derivative. There is another situation where it fails to exist. And this one's always hard for me to draw. I'm going to try my best. Before you commit to drawing it, I would suggest let's talk about it for a minute so you can see if this happens. We have functions, and I'll switch colors so it's easier to see. We have functions that do things like this, right? Okay. The derivative is a slope. It's a limit. It's a rate of change. All these different contexts. Can you tell me the slope right here? Okay? And it's still positive, right? You can tell me the slope, you can tell me the slope, everything's fine, everything's fine. I'm going to go to this board because I have more space. Everything's fine, everything's fine. Looking good, feeling good, looking good. Stop. What's the issue with when I try to take the tangent line right here and talk about its slope? What's the slope of this line?
not infinity? It's undefined because I rise infinitely far. How much do I run though? 0. We have an undefined slope. It's a vertical line. We can't talk about the slope of a vertical line. In the situation that we have here, we are just going to say sharp turns. This one fails to exist because we have a vertical tangent. If you are looking at this stuff and going, oh man, I am terrible at graphing, I don't love it, that's okay. You don't have to be perfect at graphing. We let the calculus find these things for us, but it's easy to think about and see why it doesn't exist as we look at it here. Okay, sharp turns doesn't exist. Where else? At a vertical tangent. This last one is kind of like a sharp turn, but it has a very specific name. The last one, did this picture make sense with the vertical tangent? I would maybe sketch it and say undefined, if you want to. Undefined f prime of c. Okay, this last one looks very, very, very similar to this, or to the sharp turn, I'm sorry. But let's talk about it. We have what is known as a cusp. Okay, I don't know exactly what this word means. I would think like on the cusp of greatness, like you're almost there, but I've never actually seen the definition. You guys have definitely never seen the cusp or a cusp in math and known it as such. We're going to draw a cusp real quick. Okay. Are there functions that do something like this? And I'm going to do this one in green. Something like this. And it starts getting steeper and steeper. And then maybe it turns around into something like this. And I'm going to move it over here instead. I don't know that I like separating this into its own category necessarily, because in my mind, it kind of looks like a sharp turn. Would you guys agree? However, when we look at the tangent lines, we're going to see there is a fundamental difference in how these work. We saw that the first one led to limits doing this, or derivatives doing this. The left and the right don't equal. The second one, it fails because we know that you can't find the slope of a vertical line. This one, I don't need you to draw them, but we are going to make sense of it. I'm going to draw them all. If I were to take the tangent line here, it's kind of negative, right? And if I go a little bit further, it's more negative, and more negative, and more negative. As I get closer and closer, how much more negative does it get? Is it ever going to stop getting more negative? If it really is a cusp and it folds in on itself like this. So when we look at the slope, we're not going to quite say it's just undefined necessarily, although it will be. My slope gets more and more negative, right? So if I were to check at this c value, f prime of c from left. Give me a way to write down it becomes more and more negative. It's like it approaches some number. We have a slope of negative infinity showing up. It gets steeper and steeper at negative infinity. That on its own isn't a huge issue. But when we start getting closer and closer to c from the right, notice my slopes, as I get closer to c, they're getting bigger and bigger. Are we getting closer to negative infinity with all these new slopes? What's f prime of c from the right here? F prime of c from the right, Sean says correctly, approaches positive infinity. This is very similar to this because we see the left and the right don't exist, but they don't exist because of this infinite deal rather than just different numbers. Okay, 3 ways they fail. Feel okay with those? Should we do a quick brain break? All right, so